So today I want to tell you a little bit about our work on using count-based abstractions for analyzing network contention points. But before that, I do want to introduce my student very quickly. He's the first author on the paper, but unfortunately couldn't make it to present his work because of visa issues. So Amir is a third-year PhD student at Waterloo working with me. He's both interested and very good at anything in the intersection of formal methods and systems and networks, and he's looking for internships. So if you or anyone you know is looking for great interns, please come find me. All right, so what is a contention point? A contention point is anywhere in a network where multiple packet streams are competing for the same resource. So this can manifest, for example, as a packet scheduler or a switch or anything like that. And most often than not, there is buffers at contention points to temporarily hold packets while they're waiting to get access to that shared resource, for example, to go out on a link. And there's some mediation logic that decides which buffer it gets to send the packet out next. And really, we can think about a network as a system of contention points that are composed together. So when I say we want to analyze contention points, what I mean is we want to build a verification engine that takes a contention point, so this would be a model of the buffers and the mediation logic, an input workload that is describing the traffic that is going to enter the contention point, and a query that is about really any property of this contention point that you care about, and then try to check if there's any packet trace that is going to match the workload and then violate the property or the query. So for example, contention point can be a simple round-robin scheduler that has two buffers, for example, here. The input workload can specify the rate at which packets from different traffic classes, here they're encoded with different colors, are going to enter these buffers. And the query can really be anything about this contention point that you care about. It can be about how fast the buffers are draining. It can be about how much the queues are going to build up. Or some property of this output sequence. So for example, here, we're interested to know if the red traffic class is going to get a fair share of the output bandwidth. So prior work, including some of the work that I've done, have looked into the benefits of building such a verification engine, so I'm not going to talk more about that. What I'm going to focus on for the rest of the talk is how do you model this contention point, specifically the buffers, which are kind of an integral piece of reasoning about network performance. So how do we model a buffer? So we have actually two options that are kind of at extremes. So one option is to use arrays to model them. So here you would use, let's say, an array of Boolean variables that is the same size as your buffer. And each Boolean variable is representing whether a packet exists at that location in the buffer or not. And then you can also use some metadata arrays to keep track of kind of the metadata about each of these packets. So for example, here, the metadata we care about is what traffic class these packets belong to. So we can have an array that tracks whether a packet in the buffer is from the red traffic class or the green traffic class. So this is a good model easy one to use because it allows you to kind of very precisely track the order at which individual packets have entered the buffer and gotten stored there. But the problem is the model size and complexity is a function of the buffer capacity. So the bigger your buffer, the bigger these arrays are going to get, and the more variables you're going to need to model the buffer. And that becomes problematic. Actually, we see in our evaluation that really beyond buffers that can hold about tens of packets, this really doesn't scale. And in the real world, you have kind of hundreds or thousands of packets in a buffer. So that's one option. The other end of the extreme is just using counts. So here, instead of individually tracking packets, you want to keep track of how many packets of each type is there in the buffer. So the good thing is the model complexity is going to be independent of the buffer capacity. No matter how big your buffer is, if you only care about these two traffic classes, you can just use two integers to represent what is stored in the buffer. But the problem is this is too imprecise. And I'm going to show you why with a very simple example. So here in the middle is the buffer, and we're using counts to represent what is stored there. On the top, I'm going to show you the order at which packets are entering the buffer. And at the bottom, the order they're going to leave the buffer. And for the sake of this example, every logical time step, we have two packets coming in, and we dequeue one packet. So let's say at the beginning you get one red and one green packet. You update the buffer counts accordingly. So when you want to decide what to dequeue, the buffer doesn't really know. It knows it has one green packet and one red packet. It doesn't know at what order they entered. So it can really pick, without us putting more constraints, it can really pick whichever one it wants to send out. So let's say it picks red. Next time step, you get another red and another green, update the counts in the buffer. Again, the buffer can just decide to send out a red packet. And you can already probably see what the problem is. If this traffic pattern continues, every time there's a dequeue decision, you have both red and green packets, the buffer can decide to just output a red packet. So here, our model is actually allowing a situation where green packets would never leave the buffer, and you would only have red packets in the output. So basically, it allows for arbitrary reordering between the enqueue and dequeue sequences of this buffer. And clearly, we don't want that. There's an example, if you're interested and we have time at the end, I can talk about kind of examples where very simple properties, like a verification engine with this buffer model would not be able to verify very simple properties. Okay, so back to this picture. We had the arrays on one end, counts on another end. Is there something we can do in the middle? And the answer is yes. What we do in this paper is to propose a model that allows you to navigate this entire trade-off space between precise ordering and no ordering at all. So I'm going to use the same example as before to kind of walk you through our model. So our solution is to use a combination of counts and windows. So we're in the same setup as before, but here we're going to track two more sets of counts, one for an enqueue window and another one for a dequeue window. So the enqueue window is going to track kind of packet counts for a finite number of packets at the beginning of the enqueue sequence. And the dequeue window is going to do the same thing for a finite number of packets at the beginning of the dequeue sequence. And the window size in this example is 4. And there's in the real model, there's a lot of constraints, but the ones I want to focus on here is first that the counts in the dequeue window are not allowed to exceed the counts in the enqueue window. And the difference between the counts in the enqueue and dequeue window is what is left in the buffer. All right, so with that, let's walk through the same example as we had before. A green and a red packet come in. We're going to update the counts in the enqueue window and in the buffer accordingly. And when it comes dequeue time, at this point, the buffers can decide to dequeue either red or green and still stay within the constraints that are on the slide. So one more time step, we get another red and green packet. Again, the buffer can dequeue a red packet and still stay within the constraints that are on the slide. So now, and what I do want to point out here is that still we're not enforcing any ordering, right? So within a window, if you look at the enqueue and dequeue window, packets are actually in very different orders. So now we're going to get 2 more packets. Here what happens is that our enqueue window is actually full. It already has tracked 4 packets, and we know that not all 4 packets have left the buffer because the counts in the enqueue and dequeue window do not match. So what we're going to do is we're going to start a new window. We call it an overflow window, and we're going to track these new packets there. And this is where we're kind of putting an ordering barrier, right? So we're saying, we're going to track these new sets of packets in the new window, and until all the packets in the first window have left, we're not going to consider any of the packets in the new window for dequeuing. And this is going to show up when we want to dequeue next. So at this point, even though that red packet that is in the overflow window is actually there in the buffer, when the buffer wants to make a dequeue decision, it has to dequeue it. Whoops, sorry, what did I do? Okay, it has to dequeue a green packet because if it dequeues a red packet, the counts in the dequeue window are going to exceed the counts in the enqueue window. So here, our buffer constraints are going to enforce that a green packet is dequeued. And the same thing is going to happen next time. Again, when we want to make a dequeue decision, we are still forced to dequeue a green packet so that the counts in the dequeue window do not exceed the counts in the enqueue window. So at this point, if you look at the enqueue window and the dequeue window, the counts match. So we're sure that all the packets from the first window have left the buffer, so we can safely move on. the overflow window is going to become the new enqueue window, and our dequeue window is going to reset to 0, and we're going to keep doing this kind of for the future time steps. So one thing I do want to point out here, again, if you look at kind of these packet sequences, you can see that ordering is not enforced within a window, so there's still reordering possible, but it is enforced across windows. All right, so this model is parametric by window size. So if you have a window size W, we're sure that the reordering is actually bound by the window size, or W minus 1. And if the buffer capacity is C, we're going to have to track these many windows. So one enqueue window, one dequeue window at any point in time, and C over W overflow windows for when some packets have not left the buffer and new packets are still coming in. So you might be wondering, what window size should I use? And the answer is that it depends, right? This is a model that is parametric and allows you to navigate this trade-off space. So if you pick a smaller W, it means you want to kind of track ordering in a more finer grained manner. But that means that you might end up with a more complex model, for example, because you have to track more overflow windows. And in fact, if you set W to 1, you kind of reduce this to a very precise model that is tracking the ordering between every individual packet that comes in. So what do we do in our evaluations that I'm going to talk about next? Well, we recommend that you set the window size to the buffer capacity. And this is because we believe this is allowing you to capture just enough ordering information with relatively low complexity. And why is that? On the precision side, the intuition is you usually set your buffer sizes kind of based on the maximum expected size of a burst, right? So if you set your window size to the same as the buffer capacity, it's basically you're saying, I don't really care about capturing ordering between packets within a burst, but I want to capture ordering between packets across burst. And packets within a burst usually anyway arrive close together in time, so it intuitively feels okay to say, I'm not going to care about the ordering if they all came closer together in time in a burst. So that's from the precision side, why we thought it makes sense to set the window size to be equal to buffer capacity. And on the kind of model complexity side, if you set it that way, you only need to track one overflow window, so 3 windows in total. So that's actually relatively lower overhead. And this actually shows up in our evaluation. So what we do in our evaluation is we take some kind of case studies of contention points and workloads from FBIRF, which is the closest related work that was published at NSDI a couple of years ago. And we keep increasing the buffer size and kind of watch the trend. And this confirms kind of what we expected, which was across workloads and case studies, the count-based model verification time is largely insensitive to buffer capacity, whereas the array-based model, it kind of fluctuates and it ends up having exponential growth at some point. And the other thing that this confirmed was our count-based model can be precise enough. By setting the window size to the buffer capacity, actually for all these case studies, we got the same verification result as FBIRF. So this was precise enough. One thing I do want to point out is that kind of we observed this across all our case studies, but it showed up kind of better in this particular one for a fair queuing scheduler. Was that there's really no one-size-fits-all buffer model. So specifically for small buffers, the precise array-based model ended up doing better. And what I think that the kind of the reason is our count-based model has to do integer arithmetic, whereas the array-based model, if it's a finite array, it doesn't really have to deal with integer arithmetic. And I think for smaller buffers, the overhead of integer arithmetic kind of takes over. So it's not worth it for that. But for larger buffers, the count-based model starts to do much better. And even there, there are situations where you don't need this whole windowing mechanism to enforce any ordering. For example, if you're looking at a standalone scheduler, and you have kind of buffers where each buffer has only one type of traffic in it, you can actually forego the windows and just use kind of simple counts. So after observing all of this, we made sure when we are kind of modeling our contention point to decouple the buffer and the mediation logic with a minimal interface that allows us to swap in and out different buffer models quite easily. And it also has this nice side benefit that we can actually derive the mediation logic from some higher level C-like programs. So I won't have more time to talk about this, but there's a lot more in the paper about how we kind of do this translation. We talk about some more trade-offs between different buffer models using a small leaf spine network, and some extra discussions about kind of AQM, delay-based properties, and non-FIFO buffers. So I'm going to end here with some takeaways. So buffers are an integral piece in analyzing network contention points. And there is a trade-off space between how much ordering do you capture in a buffer and how complex your model is going to be. The counts plus windows model that I presented kind of gives you a simple but powerful abstraction to navigate this trade-off space. We do find out that no one model is going to fit all the situations. So decoupling the buffer and mediation logic kind of allows you to both try out multiple buffer models and try to use high-level languages to express these contention points. And with that, I thank you, and I'm happy to take questions.